the origin of electric and magnetic fields. Despite all of the wonderful technology that we live with that use electricity and magnetism in our everyday life, we tend not to have a lot of personal or direct experience with these forces of nature. We have lots of experience with gravity. We have lots of deep intuition about how the gravitational force works, but the electricity and magnetism are inevitably more abstract, so in order to make sense of them, we tell a story and we come up with metaphors, analogies, and the representations, okay? So today, I want to continue to think about the electricity and magnetism, these two forces of nature, and try to make some of more sense about what they have in common with each other and with gravity, and what's different about them. In particular, I want to start to lead us towards the question of where did they come from. Once we begin to see this, we see that the electricity and magnetism are connected to one another. It's going to lead us down the path where we are headed for the next couple of lectures, in which we understand the unification of electricity and magnetism and many more pieces of physics together. Wow. So I'd like to begin today by talking a little bit more about magnets. So we introduced them a couple of lectures ago, and I hope you've looked for some magnets to play with it and just to muck around with. Magnets can be found in nature. The ancient Greek found lodestones which were magnetic. They would attract one another and in a different orientation repel one another. Just like the toy magnets you can buy at the store today, the Chinese discovered the magnets many thousands of years ago. Wow. The Chinese had compasses before the Western world had developed this technology, and you discover when you start looking at and playing with magnets, and that they have some unique properties. First of all, you have to find one. Once you found one, then you can create a new one. The easiest way to do it is with iron. Go to the hardware store and buy an iron nail. You can rub it with a magnet, and as you rub it, you will find that the iron nail becomes magnetized. It becomes a magnet. Yes. So let's think about a little bit about magnets and how they work, and I'd like to do the compare and contrast thing with magnets and static electricity. Yeah. So we already did this a little bit. I'd like to think a little bit more deeply about the differences, so that when we see the commonalities, we recognize how remarkable it is that electricity and magnetism have anything to do with one another whatsoever. So if you look at the magnet, you will find in general that it has two poles. Now, if you look at the kitchen magnet, you may be hard pressed to figure out whether the North Pole is and where the South Pole is. That's why I encouraged you to buy the rod magnets. If you look at carefully, you will discover that there are North and South Poles on the kitchen magnets. It's just that they come in the strips North, South, and so it's a little bit more difficult to notice easily. Yes. If you buy a bar magnet, it will usually be labeled. There will be a north and south and south end, and you will find that like magnet poles repel, just as like charges repels, and opposite magnet poles attract, just like opposite electric charges attract. Yeah. So once again, it looks like action at the distance, and this is a beautiful part about buying those toys. If you hold two magnets together in the repulsion orientation, you can just visualize that magnetic field is the most kinesthetic experience of an action at distance force that I can think of. A very nice feeling. You touch them and you can really visualize that force field is between them. So if you start investigating the magnets, you discover that only things that respond to magnets is other magnets or iron, which indeed is becoming a magnet when you hold the magnet close to it. A compass needle is just a little magnet, and the compass needle will swing around and point so that you can use the compass needle to detect the magnetic field, just like as we use a little charged up test object like a balloon to measure electric fields. So you could map out the magnetic field in the room, and the easiest way to do this is, it's kind of fun, would be take a magnet and lay a piece of paper on it top of it, and then go to a hardware store or maybe a scientific supply store and buy some iron fillings. If you have somebody who works in a metal shop, you can find some metal iron fillings. So you want them to be very small and light and iron, so that when they are in the presence of the magnetic field, they become a little compass needle, right? You just sprinkle them on the paper and you'll see that before your eyes the magnetic fields lines appear, because each little iron filling lines up with the field lines. Yes. So field, remember, represents the force right there on this object, and so all of the little things line up because they are so light. If you jiggle the paper a little bit, they form these beautiful field line patterns, just like the field line patterns that Faraday was drawing in the abstract. You can see right there in front of your eyes. It's very manifestly physical, and that's a nice thing, right? Yeah. Wow. So it's a little bit tougher to do this with the electrical field, because there is not a simple object that will line itself up like iron fillings do with the magnetic field. Although if you are clever, you can come up with various materials that will visualize electric field. How so? Magnetic fields can be very strong, and that helps in the story, because if you buy a bulb magnet, there is a really intense field right next to it. So there are some of these commonalities between electric fields and magnetic fields, but also some very clear differences. You cannot create a magnet by rubbing anything with anything, right? Most materials are not magnetic. It's only very special materials, and once you have a magnet, it tends to stay magnet for an arbitrarily long period of the time. The kitchen magnet don't wear it. Compass needle do not deflect in the presence of the electric charge. If you charge the balloon on your sweater and hold it near that compass needle, there will be no impact. The magnet is neither attracted to nor repelled by the electric charge. You can stop right here. We have just proved without doubt that the electricity and magnetism are completely different, unrelated forces of nature, because if magnets were doing their things, if they were attracting and repelling because of some little build up of the static charges inside of them, you could convince yourself with this one simple experiment that it's not a static charge inside of the magnet. It's some different physical thing. Why? So now I encourage you to think about lots of experiments, because there is lots of different ways that you could convince yourself of this idea. Here's another one. Earth is a giant magnet, and you can tell because the compass needles always point in the same direction. But balloons don't all float in the same direction. There is no attraction of the electric charges to magnets, just as there is no attraction of magnets to static electrical charges. It doesn't work either way. Right. Here is another big difference. In fact, it's a huge difference between the electricity and magnetism. You take that balloon and charge it. It's all negative now, and I can hand it to you, and you can walk away with that balloon. We have separated charges in the universe. We didn't create them, but we did separate them. Now you have an isolated negative charge. You could imagine, at least in principle, holding a simple electron between your fingers. one isolated electric charge, right? Okay. So you cannot do this with magnet. You cannot do this with magnet. You might say, well, why not? I'll just buy a bar magnet and I could try this experiment and take a hacksaw and split it in half. I'll put the two pieces apart, and I have a magnet north pole and magnet south pole. Well, I encourage you to try it, and what you discover is that you don't have a north pole and the south pole. You have two smaller magnets. You have a north or south and north or south, and when you separate them, you still have two little smaller magnets. You didn't isolate a north pole. You simply created a new north and or south pair. If you could isolate magnet pole all by itself, physicists have given this name even though we never found it in nature. It would be called magnetic monopole. So you can't find it in the nature. So magnetic monopole, a single magnetic pole. A magnetic monopole would be just like a single isolated electrical charge. We have not found it, which means there is a big differences between electricity and magnetism. With electricity, you generate electric field from an isolated electric charge, but you don't generate magnetism from the isolated magnetic charge or monopole. So there is something quite different about them. So here is the bottom line. If you got an electric charge, they interact with other electric charges, they attract or repel. If you have a magnet, it will interact with other magnets, they attract or repel. If you have a mass, it interacts with other masses. That's gravity. It only attracts. Okay, right. So these three forces seems to be living in their own little world. They deal with their own special materials. Wow. They seem to be completely distinct and unrelated except for slight mathematical similarities. So except for the slight mathematical similarities, like the fact that electricity and gravity both decrease like 1 over distance squared, magnet, it turns out, decrease at a different rate, and we have to come back and think a little bit about the origin of magnetic fields to make sense of that. Okay. So in the early 1800s, this was the state of physics knowledge about electricity, magnetism, and gravity. We understand the basic principle. They seem to be separate and distinct things. And then in the early 1800s, is a scientist named Hans Ørsted in Denmark was preparing for one of his classes when he was lecturing to the student about these new esoteric laboratory phenomena of electricity, batteries and compasses, needles. He was going to do everything all at once up on the stage. So he had a battery and some wires. He could close a switch so that electric current would flow through the wires. So he could talk about electrical phenomena. And he had compass needle up there. Wow. Yeah, I know this story. Yeah. So what he discovered by accident preparing for a class was that when he closed the electrical switch so that electrical current was flowing, the little compass needle twitched. This was a huge surprise to Ørsted. Apparently he showed it to his student and they were relatively disinterested because it wasn't going to be on the test, but Ørsted recognized that Ørsted recognized that this was a fantastically interesting phenomenon because remember, up to this point, electricity was electricity. Yeah, okay? And charges talk to other charges, magnets talk to their other magnets, and there is no interconnection. Now we see an interconnection. See? we see that flowing electric charge in the circuit do make a magnetic field. They attract a magnetic compasses needle. So this is a big change in the way people are thinking about electricity and magnetism. All of a sudden you have this very simple experiment, totally easy to reproduce in other laboratories, and it starts generating an enormous amount of the interest. Lots of scientists were excited by electricity. It seemed that it had a lot of promises in the early 1800s. There is this famous quote, which may be apocryphal, in which government ministers spoke to the Faraday and said, of what use is this electricity phenomena? I know that. And Faraday said, I am not sure, sire, but someday you will tax it. It's very insightful. It is a true story. That's right. So people are experimenting, they are mucking around, they are thinking about how to use the electricity thing and how to use this magnetism thing. So now you see this connection. You can close a switch over here and mechanically it's very easy to close the switch and the current flows. So now you can make a solid material object such as an iron bar rotate. You can cause a motion with electrical and magnetic phenomena. Once you can make a motion, now you are thinking engines and dynamos, all of these practical applications. So what a wonderful idea you got at your fingertips. We really need to make sense of this, because if you want to manipulate it, you really need to have some underlying picture of what's going on. So one of the reasons I love playing with magnets is that because they feel like magic. I love that the kinesthetic feeling and making sense of this feeling and controlling it. It is a part of the sort of philosophical drive. I think for this period of time, it's partly practical and partly just this curiosity about what the heck is going on here. Andre Ampere, who I mentioned before, we named the unit of electric current after him. Is a French mathematician, and he is interested in this experiment science. Okay, so he begins to do some experiments, but largely he is doing theory. He is looking at data, and he begins to formulate a law of nature that explains the magnetic fields, very much as Coulomb created a mathematical law of nature that explained the static electricity. Wow. So here is a bottom line of Mr. Ampere law. Static electric charges sitting still create electrical field. If you think of a pattern, the field lines, they emanate from the electric charges. They start at the positive electric charges. They run away and they end at the negative electric charge, or else they run off to the infinity. Ampere discovers that the magnets are quite different. You can look at the magnetic field lines, and let's think about Oersted experiment, the one where you have a wire with current running through it, and let's have a long wire. Let's have a long wire that goes from the floor up into the roof. This is a big experiment, and now let's have the wire run through a hole in the table, and you take your piece of paper and sprinkle some iron fillings on it, and ask the following: what will be the pattern of the magnetic field produced when the current is running straight up the wire, and you have these pieces of paper around the wire? Okay, so you might think by analogy to electricity that you would see radial magnetic field lines pointing away from the wire. That would be a natural response, reasonable guess, and it's completely not what you see. So what you would see in the laboratory would be circle running around the wire. The little iron fillings show you the magnetic field. A little compass needle would verify that it is the direction of the magnetic force, and it runs in a circle around the wire. It doesn't begin or end anywhere. a circle has no starting point and no ending point. This is a huge difference between the electricity and magnetism. So electric field line begin and end on electric charges, but there is no physical analogy for electric charge in the world of the magnetics. There is no magnetic monopole. So magnetic field lines are different. And when I look at the magnetic field line, sometimes I think of sometimes I think of it as allows carry with them a little risk, because you think of something flowing. Fields are not flowing. The field is static. Yeah, the field is static. The charge is flowing, but it just creates a pattern in space. The magnetic field is just sitting there. So the charge is flowing, but it just creates a pattern in space. The magnetic field is just sitting there, and when you draw it, the shape of the field is circular. So as you go further and further away from the wire, the magnetic field is weaker and weaker. Ampere again wrote down the mathematics so that we could predict the magnetic field generated from any current going in any direction of any strength. Wow. So this effect is very real. It's not that hard to reproduce. I would put it at the level of the good, hard, high school science fair project. If you try to go to the basement and see this for yourself, you have to realize that there are a couple of difficulties. One is that you need pretty hefty currents, and the currents can be dangerous. They'll heat up wires. You might set things on fire. You'd probably need a car batteries in order to generate kind of a current that you are interested in. So you'd want to use some care. There is another element of the experiment that makes it a little bit difficult, and that is that there is always the Earth's magnetic field. So if you are creating your own magnetic, so if you are creating your own magnetic field, you are always superposing the one you are making with the one that already there. So Earth's magnetic field, right? So what's the result? And what's the result when you take the two magnetic fields and you put them on top of each other? Well, it's back to the Galileo's superposition principle. Wow, it is just as if you have two forces acting. If the two forces allows act in opposite direction, they can cancel out, and if they act in the same direction, they add up, and you have a twice as big of force. It's the same things with the magnetic field. If you have a magnetic field from your current in the wire, you have a Earth's magnetic field, and if you are aligning things so that they are both pointing in the same direction at some given points in the space, you'll have a doubly big magnetic field. But if you have allied things so that they are in opposite direction, you won't have any magnetic field at all in that point in space. Wow. So this is other difficult things about the experiment, making sure that you are separating the natural field that already there in the room from the created field that you are trying to study. Yes.